This is the problem about the thermometer, and it says, ideally, when a thermometer is used to measure the temperature of an object, the temperature of the object itself should not change. However, if a significant amount of heat flows from the object to the thermometer, the temperature will change. Here we're going to calculate something where, the thermometer itself, as we're putting it into water, does influence actually the temperature, so it's going to change the temperature of the water. Notice that in the lab on specific heat capacity, where I'm asking you to write down as many errors as possible in your conclusion, that would be one. We didn't determine the mass of the thermometer or figuring out what original temperature it was, and kind of neglected its effect on that it has mass and therefore specific heat, its effect on the experiment itself. So as I said, for that one, write it down as an error. Here they actually let us calculate what the effect is. Anyway, I haven't finished the problem, so it continues on. A thermometer has a mass of 31.0 grams, a specific heat capacity of 815 joules per kilogram in Celsius degrees, and a temperature of 12.0 degrees Celsius. It is immersed in 119 grams of water, and the final temperature of the water and thermometer is 41.5 degrees Celsius. What was the temperature of the water before the insertion of the thermometer? Okay, let's see what's given. The mass of both the thermometer and the water are given. The specific heat capacities of both the thermometer as well as of water are given. I mean, it says in here, it's water, so you look it up. And the one for the thermometer is given as 815 joules per kilogram in Celsius degrees. And when you look in the table, it's pretty close to what glass is, so that makes sense. Using a glass thermometer with some mercury in it. And then we are supposed to figure out what the temperature is, but in all likelihood we should figure out what the temperature decrease is for the water. And then take that one and add it to the final temperature of the water to get the original temperature of the water. So this one here we're trying to figure out. So let's see where we start. For the thermometer itself, we would have that Q equals the specific heat capacity times the mass times the delta T for the thermometer. And now we have to see, well, this delta T, what we're supposed to figure out here is for the water. What about the thermometer? Well, that's actually given in the problem. So where it says that the thermometer starts at 12 and then it warms up to 41.5 degrees Celsius. So that means that the difference of 29.5 Celsius degrees is a temperature difference for the water, so that one is given. So one of them is given and the other one is what they're asking for, and we can kind of see that we have 6 variables, 5 of them are known and only one unknown. Okay, so this one here is the thermometer. Then for the water, it's the same kind of equation, equals C times M times delta T. Okay, that was supposed to be looking a little nicer. So there's the C for the water. And then we realized that the water being at a higher temperature than the thermometer is, the amount of heat that flows out of the water and the amount of heat that flows into the thermometer are equal. That, of course, has to do with the conservation of energy. So whatever heat flows out, which we don't have to calculate that, but simply what we have to say is that the two heat flows are the same, so the heat flow into the thermometer is the same as the heat flow out of the thermometer, out of the water. And yeah, technically this one here should be negative and this one here should be positive. And I think I can write this by saying that, this one here, the heat flow is negative, so therefore I put another negative in front of it to make this one here positive for the thermometer. We can actually say it that way because this temperature increase, this delta T is a temperature increase, so the whole thing is going to be positive. This delta T is a temperature decrease, so the entire so the entire heat is negative. So I'm going to write it like this here, and then I'm going to plug everything else in. So it's C times M times delta T for the thermometer, and that equals then negative C times M times delta T for the water. Could have also written H2O there. So delta T for the water therefore comes out to C M delta T for the thermometer. This one here all being given 815, 31 grams, and that was 29.5 degrees Celsius. And here we have C, the 4,186, and this one here is 119 grams, and there's actually a negative in front of this. And then, oh, by the way, this one here being in grams and this one here being in grams, that's why we don't have to convert it to kilograms, because the grams readily divide out. I'm going to make this negative hopefully look a little nicer. Okay, so that way here, yeah, this one here being 4,186, this one being 119, you come up with something, and this one here is then going to be the temperature decrease of the water in Celsius degrees. It's going to be in a neighborhood of a little bit less than 2 Celsius degrees, and that's by how much the temperature decreased. And then of course we would have to add that number here, or subtract the negative number, to the to the final 41.5 degrees Celsius, and therefore, yeah, so subtract this one here, and this looks kind of weird. So therefore we're going to come up with something like 43 point something. Again, my 4 always looks miserable. So 43 point something, you'll see that that's what you come up with, the original temperature of the water. Again, that temperature difference, this one here being the original, this one here being the final temperature, means that there was a temperature decrease, and that's why this one is a negative. And again, that negative arises from here and originally here, because this one is a negative heat flow to begin with out of the water. This one is into the water, into the thermometer, so this positive, this one being negative. It needs that negative in order to make these two sides equal.